I assume that you all looked at the Friday's lecture. Today is actually a continuation, but in case you did not look at it, you don't have to walk out, because this is, to some extent, reinforcement learning is continuation of MDPs in general. It's not exactly a continuation of policy iteration that we discussed in the last class. Okay, so actually, originally I thought that I would actually have started reinforcement learning on Friday, in which case it would really have been a continuation. But since I went slow enough, so it's actually slightly loosely coupled. But anyway, so it's very much connected to the topics that we were looking at. The topic we were looking at, which is Markov decision processes, and reinforcement learning is a general idea, which is basically, in some sense, you're behaving, and after you do a certain amount of behavior, you get some reward. Okay, so you basically do a whole bunch of actions and you get a reward at the end, and you are trying to figure out sort of what did I do right or wrong to get this reward. Okay, and from that you will slowly modify your own behavior. In fact, the reinforcement learning, the term came from psychology literature, and B.F. Skinner is very well known for his belief that essentially we just come with a big old MDP, essentially, and just learn everything by being given reinforcements. And clearly rats seem to do that. You can actually give shocks to rats and cheese to rats, and they seem to learn basically what's the right action to do in the maze, to get the rewards. Okay. Now, of course, the only thing is, interestingly enough, you must somehow depend on the evolution to have hard-coded rewards into your the body, because if in fact the rat is one of these masochistic rats which likes shocks and hates cheese, then it will learn a behavior, but it's not exactly what you're hoping it will learn. Okay. Mostly we come in, the psychological theories, and I should be the wrong guy to talk about psychology, but the general idea is that we come in with built-in reward systems, and essentially to get us to do right things, we basically, overload on top of those reward things. So you do a bunch of actions and you get a reward, and then from that you sort of figure out what to do. Now the problem with this, the computational difficulty in this work, in this view of learning, is what's called the credit blame assignment problem. So you do a huge number of actions and then you get reward. In fact, one of the most, so in some sense, from a reinforcement learning point of view, scenarios where you get reinforcements pretty much immediately after your actions are much better than those in which you get reinforcement too late. Okay, and this should not be too surprising, but the world itself may be such that you get reinforcements only like way down the line. So for example, if you're trying to learn chess game, right, essentially any single move may not necessarily end the game. You do a huge number of sequence of moves at the end of which you may win or lose the game, and then you're trying to figure out which moves from what states are the right things to do. Do you see what I'm saying? Now, for the longest time, actually, people have, of course, considered reinforcement learning as an important thing to study computationally. Psychologists always assume that, if you just set the reinforcements correctly, then any behavior can be learned. And there is a famous, partly apocryphal, probably I hope, legend that Skinner put his firstborn in the Skinner cage and would give little reinforcements until the kid learned the right sides of behavior. Okay, so he really believed in that reinforcement learning would be the way to understand psychology. Okay, human psychology. But computationally too, people actually try this lots of different ways. In fact, one of the very early ideas is, this is TD Gammon, but I'm just showing you this, but one of the oldest AI programs is what's called Samuel's checkers playing program. And basically Samuel set it up as, without knowing at that time, he wrote a program, okay? But if you were to look at that program from our modern understanding, you can see that he set it up essentially as a reinforcement learning technique, okay? Where the program plays against itself multiple times to learn what's the best way to play checkers, and then improves its performance so that then it can play better against humans. Okay. More recently, among the same things, is this backgammon, TD backgammon, which Samuel's actually was from IBM, so the interesting connection. And Jerry Tesoro, who wrote the TD backgammon, he essentially did again one more reinforcement learning program for essentially learning backgammon, which is again, I won't try to explain to you because I don't know what it is. You can figure this out. And then essentially once again, partly what it did was it does self-learning through simulation, okay, and then do lots and lots of simulation, and from that experience got through the simulation, it learns how to play the game. Okay. In fact, one of the interesting questions that you will see as we do reinforcement learning is, until we came here, we knew the following distinction. We knew there is an agent, and there is a brain, and in the brain you can think. You're thinking about what happens to the world if I were to do this action. Do you see what I'm saying? So that's like mental simulation. That to be able to do this, you need a model of the action. Do you understand what I'm saying? If I want to say, okay, what will happen if I do action A1 and then action A2, then I need to know what are the possible effects action A1 has, what are the possible effects action A2 has. Okay, you knew this. And then you also have, if the brain is too small, you can just, this is the environment, the world in the raw form, and then you can actually do the action in it. And then it will tell you what the action did. Okay? Many a time, unfortunately, by the time it tells you what the action did, you probably cannot exploit what happened because you're dead along with the action. You see what I'm saying? Because when you do the action in the environment, if the environment is non-ergodic, then when you did the action, you die. Right? That's why thinking is important, because you die in your head, it doesn't matter. You still live to see another day. You die in the real world, you die. These two you know till now. And one of the things we'll see as part of reinforcement learning is this idea called a simulator, which is not surprising to you, right? So the pilot, Sullenberger, has a brain, hopefully, does have an environment, he knows how to fly over, he actually can do various actions and see how the flight goes. But also, before you give him, the environment, they give him the flight simulators. And the flight simulators, what's interesting, of course, especially in flying, the simulators, they spend so much time in making the flight simulators that they're extremely realistic. Okay? Not extreme, very close to realistic, at least, presumably. And so people first try, flying on the simulator. Okay? Now what's interesting, of course, is no pilot is ever allowed to fly without actually having done humongous amount of these flight simulator things. How many of you did driving simulation before actually driving on the rural road? Why?
Does Need for Speed
Obviously,
count?
what?
Does Need for Speed count?
What needs for speed?
It's okay.
Yeah, because you want to start right doing, and then you assume that a few people here and there dying, it's okay. You know, it's like one of the things that I cannot get over is if a flight falls down and one person dies, it's big news. Whereas if I just run over various people, it's usually small news. It's only local papers, you know, report it. You know, so somehow, you know, people flying dying has higher importance than people walking dying. You know, it's just less important. Anyway, the important thing I want to say is simulators can potentially be made for driving too. And you might want to think in the background as to why are we being given free driving licenses. Of course, for the current generation of kids, I guess, you know, they are playing these quote-unquote video games, and presumably that's giving them simulator skills, you know. So it's like you get into the car and say, where is the up arrow, where is the down arrow, you know, where am I going? But anyway, so it is, if the task is important enough, sometimes somebody will sit down and write the simulator for it. And then, if you don't have the model of the world, you can try your actions in the simulator. And when the simulator dies, you don't die. You just reset and restart again. Do you see what I'm saying? And that helps learning significantly. You know, having a simulator, access to a simulator can help learning. Okay? The best is actually being able to just figure out in your own head, you know, what happens. But if that doesn't, if you sometimes, in some cases, essentially the best you can do is a simulator. That's one of the things I hope you will get as part of the discussion. I'm going to get to you. As part of the discussion of the reinforcement learning. When do you go with a simulator as against world? I mean, as against model or world? So on one side of the simulator is the model. If it's a model, you can put it in your head. So the mind itself is the simulator. Okay? And if it's the world, it's the world. In which case the world knows best what the world is supposed to do. Yes, sir.
So for the simulator, you need to have a model of the world. Right?
Yes. Interesting. Yes, that's true. Okay. However, sometimes that's actually a very good question, and you need to think about this. You know, and it's not obviously the answer is not upfront obvious as to why you need to have a separate simulator. Sometimes you can write simulators which basically will wind up writing imperative programs, okay, like procedural programs, right, as against models which are declarative. You see what I'm saying? So imagine people actually know how to write, you know, physics-based simulators for, you know, airplanes. But it's very hard to write them in terms of actions with their effects. Sometimes the model is actually much bigger than the simulator, much more cumbersome than the simulator. People just give you the simulators. Okay? And so that turns out to be the important difference, actually. Okay, sometimes actually the reason you won't use a model is because model can actually be quite, you don't know the language in which to write the model such that the model is compact. Do you see what I'm saying? Okay. Any other questions? So this guy, you know, backgammon actually has a simulator with, you know, for the game, and it just plays over the simulator, and it can play as many times as it wants when nobody is around, and then it improves its performance with respect to the simulator, and then it can play against the real opponents. And having simulators is actually quite useful. Okay, one of the interesting things is in real world that we live in, well, I don't know, of course, backgammon is part of our real world. But there are parts of our real world for which there are no simulators. Right? And so, especially one of the things that we have in the back of our head when we're discussing reinforcement learning is how do infants learn about the world? Because they come in with some knowledge, they have these actions, they know what the actions they have, and they're trying to figure out when to do what actions. Okay? And then infants cannot actually simulate because there's no separate simulator. Either they know the model or they don't. Okay? Of course, there are crazy ways in which I could say, for example, kids asking parents, so if I do this, what do you think will happen? Okay, so if they learn language, they can use the parents as the simulators, standing. Okay? So rather than do it themselves, they'll say, you know, if I do this, if I, like, you know, slap my teacher, what do you think will happen? Which is better than they going and doing it. Okay? And before they actually learn to speak and communicate with their parents, they actually just have to try out and see what happens if they slap the kid at the start of the teacher. Okay? But anyway, so that's TD Garman, and that's also a reinforcement learning algorithm, and that also learns by. So one interesting thing that you're learning, that hopefully you're getting out of reinforcement learning, is you need experience. You learn from the experience. Okay? Experience can be costly. Getting experience takes time. Simulators will cut down the amount of time you take for getting the experience because they're pseudo experience. Do you see what I'm saying? And also they'll have less of an actual cost. So for example, if the flight keeps falling, as part of experience, we essentially get into accidents once in a while. Okay, when you start driving right away without having, driven on the simulator, in fact, I just read it somewhere in one of these last day before yesterday or something, in some paper and some article, they were saying that X is just like driving in the sense that the more you do it, the better you become. But the first time you do it, you are terrified. Why? The reason you're terrified is because you just give like $1 to this guy who gives one lesson and then you start driving. Okay, pilots are not allowed to do that. They have to go through a lot more of training with the simulator first and then in the real world. Okay, so you need experience, and experience costs. And one of the issues in reinforcement learning is when I have experience, how much can I exploit the experience I have? Since experience costs, you don't want to throw it up. You want to use every little bit of the experience. One of the things we'll see, I'm just throwing words out. For example, you will see that some of the techniques for reinforcement learning differ in terms of how much, how efficiently they use the experience. Do you see what I'm saying? Okay. The second thing about reinforcement learning is that one fast way to get experience is if you have simulators, you can improve that. That's one point we meant to get there. And the third thing is that the difficulty of reinforcement learning in general is created by an assignment problem. How do you figure out what you should have done in this state, given that you only got big rewards or big negative rewards far away from this state? Okay, which of the actions that went from here, that took you from here to here, actually are to be blamed? Okay, and this was a big issue. People used to talk about it a lot, and then they were thinking about what's the best, framework to study them in. And one of the best things that happened for the community, reinforcement learning community, is to realize that in fact Markov-addition processes provide a great framework to study reinforcement learning. They have everything. They have reward function. They have action models. Okay, they have uncertainty thrown in. So in some sense, essentially you can study reinforcement learning in the context of Markov-addition processes. So you're trying to learn the model for MDP. Okay, and once you learn the model, then you can use the model, which is what we did till now. Yes?
So you mentioned for the reinforcement learning, we need a model for the board. So how about the model for the brain?
No, all I'm saying is you can have, in fact, one of the interesting things we find, we see is that reinforcement learning makes you realize that you don't necessarily have to have the model of the world to work well in the world. In fact, we will talk about this idea called model-free versus model-based reinforcement learning. And we'll look at this nice picture, which I'll show you once just now, so that you have some kind of an idea as to where we are going. I'm sort of going in, different orders, but this picture turns out to be extremely useful in the end, although I'll get to it after many slides, but now I'm just jumping ahead. So here is basically what this picture is telling you. Okay, you're thinking in terms of Markov-addition processes. I already said that. Okay, now if you have a Markov-addition process and you have a model for it, you know how to convert the model into value and policy. That's what you did last several classes. That's what we did. Now the question is, who gave you the model? We just assumed it was given. Okay, so the cycle is you got probably either somebody just gave you the model, or if you are just alone, all alone in the world, you learned the model from experience. Okay, so from experience you can learn the model and then use the model to get the value and policy. Now how did you get the experience? The world is out there and you have some default value or policy, default policy with respect to which you acted in the world. If you don't have any policy, that's having a random policy. Right? Okay? With respect to whatever policy you have, you acted in the world, and when you go and act in the world tells you what the consequences of your actions are. So you get state, action, reward, state, action, reward, state, action, reward. The state, action, reward triples are your experience. The sequences of state, action, reward is your experience. Okay, so at one level, the cycle is this. From value, if you have some kind of a random policy with respect to which you work in the world, you act in the world, you get, experience. From that experience, you can learn the model. From the learned model, you can learn better policy. And using the better policy, you act in the world. And you get more experience, and you can learn even better policy until you reach the optimal policy for the world. That's the cycle that you already kind of guessed based on the discussions last class. The foreshadowing I did that, RL is nothing but learning model. But then it turns out that for RL, you can also just short circuit this whole thing and so go directly from experience to policy. In which case you never learned the model to begin with. Okay, so you never actually have a compact representation of actions and what they do in the real world. You just learn the policy upfront directly. Okay, in which case you don't have this as this part of the cycle at all. You just short circuit and go directly here. And one of the interesting things that you will try to understand as part of this set of lectures is when is it better to do it this way and when is it better to do it this way. Okay, do you guys know, do you think in your real life you sometimes do the right thing without knowing exactly why it works? So then you do this. You figured out it works, and why do you, basically, I do it and I'm winning. Why do you care? I mean, I don't quite know what the model of the action is, but it works. And partly you learned it by going model free. Okay, so we'll get to that. In fact, that's part of the thing that reinforcement brings up. And one of the interesting things, of course, is if you were to figure out how to, you just happen to know what to do when in the world, you're quite good at it. Okay? And your friend knows the model of the world. And so using that, they'll compute the optimal policy and use that. You both are same as far as I'm concerned in terms of doing action in the world. What's the difference between you and your friend then? You're doing it different ways. I mean, maybe you're doing it in C++, they're doing it in Lisp. Is there more difference than that? One thing that you cannot do is if all you know is the policy, then you know what's the right action to do, but you can't simulate what happens if I were to do that action. You cannot mentally simulate. Your friend, by having this extra piece, can both do the right action and also simulate what happens if I were to do this action. If you picked up the optimal policy, there is no difference. If you're in the middle, then in fact you do need to be able to simulate what happens when I do these actions. Models give you the ability to simulate the world in your head. Okay, but you can avoid models and then go directly to work. Okay, so for those of you who have background in machine learning, kind of a loose analogy is if I were to give you a bunch of training samples and you're trying to classify these test samples, you can go directly from the examples to the classification. Nearest neighbor is one, such, for example. Okay, so you put that guy in the same space as these guys, and whichever, it's close to most of the positives, then it's positive. If it's close to most of the negatives, it's negative. Why is it so? I don't know. It seems to be in the neighborhood where everybody is winning, so this will also probably win. Whereas most of the learning actually takes the stance that there is a hypothesis which tells you why the labels have, the training samples have the labels that they have. And uses that hypothesis, first learns the hypothesis and uses the hypothesis to do the testing. So a question is, when is directly going from examples to classification better or worse than going through hypothesis to examples? That's the same sort of a question as this. Okay, if you do learn hypothesis, then you sort of learn a causal theory of the world in some sense through your life. And so you can sort of write books about philosophy of how the world evolves. If you don't, you just still can do the classification, but you don't get to quantificate as to what happens because you have no clue what happens. You just know this is the right thing to do. Okay? Okay. So as I showed last class, essentially we are still thinking, so we want to look at reinforcement learning in terms of MDP, and we basically assume we have an MDP, and the only question is, we don't have the model for the MDP. What's the model for the MDP? The reward model and the transition model. Those are the two things that are missing. Why do you need them? Because you use them to eventually get values and policies. Right? And if I give you the model, then you can get values and policies. So, in fact, actually I would say model is sort of the middle point, because if I tell you already the values, then you're happy. So if you can, somehow get to the values of the states, then you are happy, because from there you can get the policies. Okay. So the twist, of course, from the reinforcement learning point of view is, as I said, we don't know T and R. So you can't use the techniques we learned up till now to directly compute the optimal policy and start executing it. Okay, so you want to learn T and R. That's what reinforcement learning is. Reinforcement learning is. Okay, after T and R is actually quite easy to learn. You go into the state, you get the shock or the buzz, whatever, and then so you know what the reward is. You experience it directly. On the other hand, T is more tricky. Okay, we'll see that. And then, of course, we'll also see sometimes you don't even need to learn T. We can go directly to V. And then from there to pi. Okay, and so the most general reinforcement learning problem is, given just the set of actions that you have, you know the set of actions you have, and you don't know anything else, you don't know the T and R, figure out the optimal policy for that MDP. Okay, by basically doing some experimentation, and as part of experimentation you learn the value function, and then maybe you'll go from there to optimal policy. But now the interesting thing is, even experimentation, it's essentially the interesting part, of course, is at any given point of time you have an approximate idea about what the value function is for the world. That's not the correct one, but you have an approximate idea. And you use that to decide your optimal policy for that time. Okay? So that would be called greedy policy. A greedy policy basically takes the current approximation of the value as the real value function, and then finds the optimal, the action that will maximize the expected value. Okay? Now, and then after that, essentially you keep doing this over a period of time, the value function changes, and so as part of you learn more about how the model works, so the value function changes. As part of that, you also learn the optimal policy. Okay? So that's what the overall reinforcement learning problem is, but we will get to it in steps. In the first version that we will look at, we will assume that we have been given a policy. We've been given a policy. Okay? And you are just acting in the world with respect to that policy. and you're trying to learn to predict whether good or bad things are going to happen based on where you are. Eventually, are good things going to happen today or bad things going to happen today? Now, when you get to the good or bad things, you'll experience it. But if you are doing this policy again and again and again, then you should be able to expect, as you are going towards the bad things, 5 states away from it, you should already expect that bad things are going to happen to you. Now, you are a passive. This particular case is called the passive reinforcement learning, where that's the simplest case we'll start with. Okay, so in the passive reinforcement learning, somebody gives you the policy, and your policy is decided already. So my example for that is, if you're a kid and you've been put in this pram, and your mom or dad is pushing you around. Okay, so you are just an observer, right? I mean, so you come to an intersection, all you know is your mom knows which way she's going to go. Okay, and she has a policy. But then, as a kid, you will see after a bunch of time, unless you're not a particularly bright kid, you might realize that anytime your mom makes left-hand turn at this intersection, after some amount of time, you seem to be getting sweet stuff onto your mouth because she's taking you to an ice cream store. Right? Whereas if she makes a right-hand turn, that's not happening. Maybe she's taking you to a doctor's office and giving you a vaccination. So you should start at least realizing, as she makes left-hand turn, that things are going to be good today. And if she makes a right-hand turn, things aren't going to be good today. And of course, you're still very passive observer. At best, if you're a kid, you can cry. That's about the only thing you can do. Notice that it's somebody else's policy that's guiding your life. So somebody decided your policy, but you still have learning here. You're learning to predict the value of a state. Left-hand turn from this and right-hand turn from this don't have direct values themselves, but they do get you eventually into states following your mother's policy, which seem to be good for you in this side and bad for you on this side. So you learn that. That's a non-trivial learning. Okay, and that's basically where we'll start. That's the passive learning. Yes?
For example, if we had made a machine which is continuously learning, and now it has gone to a state at which we can say, okay, it has substantial learning and now it can act. So can we replicate its brain?
Well, the entire point of computer science is yes, that's the reason. Right? Because what do you mean a brain? It's just a circuit.
Okay, means
yeah,
that's
the whole point of computer science, right? Essentially, it's like if we ever figure out an artificial Einstein, then basically we can just copy it over to all the CPUs. And that's it. And then Einstein would not have any value whatsoever, because if everybody has Einstein, IDF of Einstein is 0. Okay, but that's a different story. Okay, but mostly that's a different issue. That's just across the board. The entire point of doing AI is that essentially once you figure out how to do it once, then you can just copy it over. Whereas unfortunately, once I figure out how reinforcement learning works, I still have to do this song and dance sequence in front of you to hope that you will get it. There is no direct lobotomy that I'm allowed to do. Okay, that's the big disadvantage. So eventually, again, all of you who have seen that Wall-E, the movie, know that we will just be taking rest while all the work will be done by robots and we'll just be fat. That'll be different. So we don't even have to do this course. That's the nice part by that. Okay, so here is a bigger picture of reinforcement learning. You're given the effectors and perceptors, and we are assuming full observability. By the way, that's not really true of the real world, reinforcement learning. But most reinforcement learning is hard enough that all the research is done in fully observable, with the fully observable assumption. That's not because that's the way the world is, that's because that's where at least you have some hope of making research progress. They're much more, all research is drunk searching for his lost keys under the light, right? Okay, so because that's where the light is, not because that's where you lost the keys. And so you solve problems that are tractable, and you solve models that are tractable, and fully observable is more tractable than partially observable, because it turns out that partially observable case, even planning is hopelessly bad. Okay. So anyway, so you have been given the effectors, we have perceptors, we assume full observability. Effectors are uncertain, so that's why you have stochastic dynamics. And the world itself is there, so you get to do actions in the world. And sometimes, as I said, you might have been given access to a simulator. In which case, then you can play on the simulator without having to play on the world. And it may not be a direct replacement for the world, but it might at least, improve your chances of, learning. Okay. Then, what you want to do, you want to learn to perform well. And from an MDP point of view, learning to perform well is to learn the optimal policy. That's it. Okay? Because rewards are decided by somebody else. And you just are trying to find the maximal expected reward, a policy which has the maximum expected cumulative reward. Okay, so this learning to perform well sort of involves any of these things. You may just want to learn the state values. That's what the kid in my example was trying to learn. Okay, learning action values. The kid might actually be learning that when I'm in this state, and if she does this action, things are going to be good. Okay. Learning the transition model. You actually say that when my mother tries to make a left turn, sometimes she seems to be going here, sometimes she's not actually, the pram is not working well, so it's sometimes going in a slightly different direction. That's, learning the model of the action. Okay, sometimes even after you get to the point where you are supposed to get the ice cream store is closed with some probability. So nothing sweet is happening on your tongue. So you learn that as part of the model. Okay, and then you can learn policy directly. To heck with all the intermediate things, all I really wanted to know is what am I supposed to do in any given state. And if I learn that, that's enough. Okay, these are the things that reinforcement learning focuses on. And then the dimensions in which reinforcement learning changes, we've already talked about it, I'm just going to say it once more. You can have model-based versus model-free reinforcement learning. Model-based reinforcement learning first tries to learn the transition model, and from there tries to learn the policy and the value. Model-free says, since all I'm supposed to do is know what to do in what state, why do I care about the model? I'll just directly go and learn the action to do in each state. Okay, so that's the model-based versus model-free. And then the other aspect of reinforcement learning is passive versus active. Passive means somebody already decided your policy for you. All you can do is, sort of get a foreshadowing effect. Sort of, I guess, if you have no clue about how the world works, then when you go up to the very top of the roller coaster, do you have any butterflies in your stomach? No, of course not. It's because you know what the world works. And roller coaster is again the policy that somebody else decided. The moment you get into it, it's a policy that somebody else decided. And still you are supposed to, yell at various points and, have butterflies. How does this happen? I mean, apart from the free fall, which is actually a physical aspect, you actually start seeing that things are going to happen to you. Or, masochistically good things are going to happen to you when you go to the top. Okay? So that is essentially the passive reinforcement learning. If you have no clue, and if you don't feel any fear, then you have to learn this, essentially. Okay? And that's what you need in the passive reinforcement learning. Active reinforcement learning is to actually sort of figure out the policy as well as the value. Because nobody decided a policy for you. So you have full choice. So what actions do you do? So if you don't at all like the experience of going on roller coasters, avoid getting onto one. Okay, that's possible if you have, if it's your policy to decide. So active is of course significantly more general than passive. So most normal agents basically has to deal with active reinforcement learning. But we'll first start with passive because it's an easier problem to understand. In terms of model-based versus model-free, that distinction is not as obvious. As I mentioned, they have both interesting trade-offs. Okay? This we would not talk about right now. Later on, I'll come back to this. Okay? So we'll do passive learning now with all this setup. So passive learning, basically, somebody decided your policy, and you just, when they do get you into that state, you will feel the reward because you're in the state. They are deciding what actions you are supposed to do, but you feel the reward anyway. So from that you want to learn the value function. Because there's no point in learning the policy, because policy is already known. You don't know it, but somebody decided already what it is. Okay. So no choice about what actions you take, just execute the policy and learn from experience. And the general case is active, which we'll get to later. Okay, and this is example of your mother pushing you around. I mean, a slightly different example. You don't quite know, you didn't probably have, when you were a kid, you didn't have that much of a choice over your policy. I mean, if kids have choice over their policies, how many of them will wake up and go to school? Zero. Okay? And yet they have to go to school because somebody else decided their policy. But that doesn't mean that they don't learn to detest Mondays and enjoy Fridays. And that's basically learning of the value of that state, given that my parents decided my policy anyway. Okay. Okay, so now the interesting thing, of course, is that the first idea we have for learning the value is you get experience. You essentially, an experience would be, so this is a grid world. We'll assume that, there's a policy that's being followed. And so from any state, this is the policy. If you're in this state, you're supposed to go up. If you're in this state, you're supposed to go up. If you're in this state, you go this way, etc. Okay? That's your policy that you're following. And of course, every state, you get a little reward. Maybe imagine that minus 0.04 kind of a reward. And then you get plus 100 here and minus 100 here. Okay? Actually, I think for this problem, plus 100 here, minus 100 here, and every other state, you get an immediate reward of minus 1. That's what this example is. Instead of minus 0.04, it's minus 1. Okay? So then you have this, and then imagine for now, this is again, we use the infinite horizon discounted RL basically. But in this case, we just actually using gamma equal to 1. Okay, gamma equal to 1 is not good, but we just try to use it. Okay, so what would be an experience look like? You start and do a whole bunch of actions. Either you do until you can't do any more actions in that particular experience because you got stuck in a sync state, or your simulator needed to be reset, or you just say, I would basically do 115 actions and I'll stop. That's my number of actions I'm willing to take. That's the maximum I'll ever do. Okay? So either way you get, when you do those actions, basically following policy, you basically transition through 115 states, then you got rewards in each of them. Okay, so for example, this guy started from 1, went up, actually found themselves up, and so got a minus 1, and they got into 1, 2, they did up again, they got a minus 1 reward, and so here is the state, here's the action, here's the reward they got. That's what the experience is, right? So this is one experience from here to here. Why? Because when you reach 4.3, essentially you got into 100 and then you just stop. Basically that's the sync state. Okay, and similarly here, it also got done by reaching a sync state. So these two are non-uniform length experiences, both of which ended in a sync state. Okay, so given this, what I'm trying to figure out is the value V for each of the states. I can also call it U. In this case, I'm calling it U for utility. And one idea is essentially to just see if you are in 1, 1 here, until you died, how much did you get? Minus 1, minus 1, minus 1, blah, 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 and then 100. Okay, so that means 1, 2, 3, 4, 5, 6, 7, 8, minus 8 plus 100, so 92. So starting from here, by following the policy, you got 92 cumulative reward. I'm just keeping gamma equal to 1 right now. 92 cumulative reward. In this case, I did, basically, I got minus 100 here and a minus 6. So starting again from 1, 1, I got minus 106 cumulative reward. Notice that if it's a deterministic MDP, then there is really one experience is as good as any. Right? Whereas because there is stochastic dynamics, every time you do the same action, you might expect a different outcome. And so in this case, when you did 1, 1, you still went to 1, 2, but when you did 1, 2 and you tried to go up, you stayed in 1, 2 here, whereas you went to 1, 3 here. That's what the world told you. Right? Okay? So one idea would be that if you have these many of these, experiences, so you just do, this is one experience, this is another experience, you can get about 10,000 experiences, let's say. Okay? And then I can essentially take the value for 1, 1 to be the average of the cumulative value I ever got starting from this state. That's it. That's an idea. Okay? So in this particular case, if just one experience I would have got U11 is pretty darn good. It's 92 good. But one more experience, now 92 plus minus 106 divided by 2. So it's really minus 7 is the expected value. Okay? Obviously this is the average. So unless you do infinitely many experiences, this is not expected to be the actual value. Right? Right? So basically, so this is, I found U11 to be minus 7. How do I find U33? Here is U33 and here is U33 and 3333. So from 33 I went here, I got 99. From 33 I went here, I got 102 negative. Okay? So for U33, and actually there's one more U33. There's one more here. So that's the interesting thing. I'm using experience in multiple interesting ways because an experience may have gotten me through the state more than once. So this experience got me to 33 from here as well as here. From here I got 99. From here I got 99. And from here I got 97. And from here I got minus 100. So I experienced this state 3 times. And then I kept track of what happened in my experience when I passed through this state. And these are the values I got. And so I just add them up, divided by 3 in this case because there are 3 times I looked at the state. So the value of 33 is 31. And in fact, normally you're supposed to use a gamma less than 1. So you, in that case, you would have multiplied, when you're starting here, minus 1 plus gamma times minus 1 plus gamma squared times minus 1 plus gamma cubed times 100. That's what we got. So you can do this whole thing with the gammas. Okay? And that's the right model normally. This is what I'm just showing so that it's easier to do that. Okay, so this is how you learn the value function. The more experience, the better the value. Okay, now one thing I mentioned about reinforcement learning is if you have a reinforcement learning algorithm and your friend has a reinforcement learning algorithm, the difference between you two would be determined in terms of, given the same experience, how much are you able to exploit that experience versus your friend? Because, as an oracle, I might know what is the optimal policy for the same problem that both of you are solving. And I gave you both the same amount of experience. Allowed you to have the same amount of experience. And this guy is still much farther from the optimal policy than you are, then I assume you know how to use your experience. Anybody has experience. Some people learn from it, some people don't. Okay? Some people learn very well from it, some people learn only sort of at the top level. Okay, so this idea is called the Monte Carlo estimation of value. Because you're just doing Monte Carlo experiments and then you're computing averages for each state. Okay, so that's, and you can learn the values this way, and this is a non-trivial learning. In fact, I made a huge deal in the beginning classes as to do you know anything about learning techniques at atomic level. And classification doesn't occur at the atomic level because there is no real learning, at the atomic level. But reinforcement learning is non-trivial even at the atomic level because this is atomic level. And nobody told you what the values of these are and you figured out from experience. Okay? That's what I was mentioning at that time. Now, the kind of learning that you know typically is somehow to say if your state has, what this learning is saying is if your state is 1, 1, then the value is approximately -7 based on my current experience. If the state is 3.3, the value is 31.3 according to my current experience. What I'd like to really say is if the state is a kind of a corner state, then the value is like this. If the state is next to a corner, then its value is going to be this way. So you want to talk in terms of the properties of the states rather than the names of the states, which is what you typically do, right? That's basically what you guys think of normally in terms as learning, and you can do that. That's just the next step. For classification learning, this step doesn't even make any sense. Whereas for reinforcement learning, this makes sense, so does this. Where if you now have figured out, let us say, that U11 is -7, U33 is 31.3, and you have a bunch of features for U11, that you define this state in terms of some state variables and their values. So you're trying to find some function that maps these features into the value that you found. That's called what problem? If I give you a bunch of training examples, these are the training examples. So I would know the features for the states that I already have. So U11 might be basically defined in terms of, let's say, 10 features. Feature 1 is value 5, feature 2 is value 3, feature 3 is value 7, etc. Okay? And then the value, for the total value for it is -7. So I have a feature vector and its value. That's my training data. What I'm trying to figure out is to directly go from features to value. Regression. A function over the features to value. That's basically called a regression. Right? Just as classification is a binary regression. So you're just learning, you do a regression. Okay? So the reason I put this slide here is it's not that reinforcement learning is doomed to work only at the atomic level. It is more the other way around. Reinforcement learning is non-trivial even at the atomic level. Classification learning basically makes no sense. It's trivial at the atomic level. Because you will only learn, as I said, if all I tell you is the social security number of people and their grades in this course, there's nothing you can learn. Zero, other than what I told you. If they again do this course, basically repeat this exact history, then they'll get the same grade. That's the only thing you learn, nothing more. What you really want to learn is people who basically sleep in the class or miss lots of examples, lots of homeworks, tend to get bad grades. That's what you want to learn. That's a feature-based description, which is a non-atomic description of the states. Right? And that can be done in reinforcement learning. That's just the next step. Okay, so if you know anything about regression before coming to this class, then you can still use all those regression, logistic regression or any technique over the features to fit, basically these values to those features. Find a function which fits these values to these features. And as part of that, you also figure out which features seem to be relevant, which features seem not to be relevant. That's the idea. If everything about you is completely relevant for your grade, then I don't learn a thing about you, about your experience. Okay, there should be some irrelevant features of you as far as your grade is concerned. Maybe, I hope that, for example, the color of your shirt has no connection to your grade. Right? And that basically reduces the number of things that, and so there may be other people who would then come into your situation because they can also have the same feature-based description for the subset of features. And that's what happens here. Any questions on this? Okay, so basically I told you a very simple idea, averages, and a slightly interesting idea on top of it. If you actually have feature-based representation of the states, then you can do all your, basically data mining, machine learning techniques and do regression and feel happy and say, oh, I realize that anytime I find, so for example, the kid might notice, for example, that the place where his mom is making a right versus left turn happens to be right next to a police station. So they might say, whenever I'm near police station, I should feel good. Now you may be worried that this kid will, grow up to be some kind of a bad guy. But, he's learning, he or she is learning that near the police station, there are actions that can be taken that will lead to sweetness on the tongue in the end. That's great learning. Okay? So that's basically regression part. And now coming back to this slide, which you just saw, let's look at it. And I made this huge deal about, are you using your experience to the fullest potential? Okay, well, reasonably maybe, because look, you know, at the first time when I looked at this experience, I thought only 1 3 3. But I then realized that actually there are 2 3 3s in this experience. So I used it. That way my average is more representative of my experience. That's using experience. Okay, so in some sense, what you're doing is you're basically doing empirical. What are you doing here? So we started by saying this guy is following a policy. And then we're trying to learn the value. But then in MDPs, if you know the policy, you should be able to just get the value. Why are you hanging around letting me do this, you know, mumbo jumbo about Monte Carlo? If you know the policy, you should just be able to set up a bunch of equations and get the value function. What did you need to do that? How do you go from value to policy? I'm sorry, how do you go from policy to value? Transition model. If you know the transition model, then you don't need, then you can basically go, that's another way of getting the value. Now, the question is, suppose I were to tell you that, okay, instead of using the experience this way, let's use the transition model. Okay, can you learn transition model from this? This is the same experience. You're not going to get a separate experience. This is what you got. Can you learn transition model from this? Look at this. From 1 2, I did up, I stayed in 1 2. From 1 2, I did up, I went to right. So I'm getting information about doing the same action in a particular state and what the average number of times I'm staying in the same state versus some other state. So I can take empirical averages of that, I will get the transition model. Right? My question then is, which would you think would be better? Should I be doing the transition model, then convert it using my MDP understanding to a value function, because I now know the policy, I know the transition model, so I know the value. Or should I just do what I'm doing here?
What we are doing here is better.
Okay, yes.
Yeah, in passive learning makes more sense to do this, I think, because you don't have the possibility to explore everything.
Did I say you have to explore?
No, but
No. All I'm saying is, think about this kid, okay? If this kid requires, let's assume that the kid is, the mother is reasonably busy and takes kid only once outside every day. Okay? So, how many days does this kid need to figure out that when they get to police station, good things are going to happen? That's what I'm asking. Okay? If the kid requires like a year before it figures out that, bad things, good things happen when I go to, police station. And another kid in the pram next to her is learning it in like first month itself. Then I would say this kid basically is fast in learning. You compare learners ultimately in terms of how little experience, how little training examples they need to reach the same level of performance. That's what learning is all about. So my question is, do you think that the Monte Carlo learning would converge to the real value function faster, or the one which first learns the transition functions and then converts the transition into value using policy would be converging faster? And you said Monte Carlo, which would mean that we wasted about 5 classes learning all about MDP, right? Because essentially that theory is wasted. Why do we need to know this connection? So when in doubt, assume that I had a plan. Okay, so the right answer in this case turns out to be actually learn the transition function, but why?
So it strikes me that in a passive reinforcement learning, it really wouldn't matter that much.
It does.
No,
It does.
Okay, so it will.
The reason is, by the way, the following. You act as if each of these states have their values independently decided. When you do Monte Carlo learning, you are acting as if each entity is an independent entity and you are estimating it separately. But that's not true. Values for states are highly correlated. Who correlates them? Bellman correlates them. So if two things are correlated and you're trying to learn them as independent, you will need more experience. Do you see what I'm saying? Okay? So that's the reason. So,
but it's highly probable that the transitions that we have learned won't be correct.
what?
It's quite probable that the transitions that we have learned.
No, but the transition won't be any less correct than the experience you got. So I think we are comparing Monte Carlo to transition model to learn. Again, one of the things that I'm hoping you guys going to do is part of the projects. You already have an MDP solver that you're going to be completing by Monday magically, right? As a little app, as a little program. So you can play this game with respect to that MDP. Okay, there are actually online MDP, reinforcement learning applets. I'll send you some links. But it will be better if you just play with your own program to see, instead of taking my word for it, which one actually converges faster. I'm trying to give you the reason, rationale as to why you should expect that Monte Carlo would be wasteful, because it misses the correlation between the values of the neighboring states, where the state's neighborness is in terms of the actions. Okay? And by missing that, you will need more experience. Okay? So to avoid that, you essentially do the DP-based policy to value conversion. To do that, you need the transition function, and then obviously the idea in this case is use the same experience, but now use it to compute the transition function, not directly to compute the value function, and indirectly compute the value function using the transitions. Okay, so using the same experience, if I say T33, the transition of doing the right action in section, in state 3.3 to get to 4.3. If I look at this experience, I have done this right action in 3.3 3 times. So 3 is in the denominator. And only one of them I went to 4.3. So 1 is in the numerator. So 1 over 3. Okay, now you might say, well, if you did it a couple more times, this will have slightly changed. But then I will say, well, if you did it a couple more times, your value would have changed too. The real question is, who is converging faster to the right value? Again, I want you to understand, some of you probably have this sort of thing built in already, but some may not. The trick in reinforcement learning is to exploit the experience as well as you can. Okay, so something which converges with fewer experiences is better, because that's what a better learner is. Okay, any questions on this? Again, as I said, this is like extra couple of lines more of code on your existing MDP solvers to figure out which one actually seems to work better. Okay. One thing, I don't know, maybe I would not do this right now. I'll skip over this. This is more interesting stuff, but I'll come back later. I want to do active model-based learning now. Till now we did passive model-based learning. Okay, I want to do active model-based learning. The difference now is I do not have a policy. I get to decide my policy. Using that, I will know the value. Using that, I can change my policy. So I'm doing value iteration, but in the real world. If you don't have simulator, then you can do value iteration in the real world itself. Okay, and then that would work. Okay, and then it will give you better, it will basically get you to the optimal policy, provided a few things. We'll see what those few things are. Okay, the few things, of course, are that if you get the experience, based on the experience, you pick the value function later. Okay, so for example, if I were to tell you, you initialize the policy to be something. Okay, let's say your mother initialized the policy. And you converted that policy into this transition model. And converted this transition model into the value. Converted this value into the greedy policy. Now are you lost or yet? Or not? Right? The point is, your mom did not care that you wanted ice cream. Okay, so she came all the way here and went this side. But now that you get to drive the pram, like that Simpsons, that little kid also has a little, driving thing. So if you have your own stick shift driving thing, you just pull the mom along with the car to the ice cream store. Right? So you learned the value of the state from what your mom showed you. And then you did better than her for yourself. Not good for the mom herself, because mom probably wanted to go to some bank or something. But it's good for you. You learned better policy. So you bootstrap yourself into better and better policies. Do you see what I'm saying? So from here you get the transition model. From the transition model you get the value function. From the value function you get the policy. Now the question, of course, is how do you convert the value to policy? Normally, what do you do? So experience, transition model, and also reward, by the way, because you do realize that you are learning the reward. One of the things I should have mentioned, and I did not, is that in this approach, you not only learn the transition, but you also learn the reward. But the reward is known for all the states that you actually experienced. And it's going to be the same every time you go to that state, because the reward is deterministic in the model we are using. Okay? And if you have T and R and pi, then you can compute V. Right? So from experience you get approximate T, and then real R, actually maybe approximate R. Why approximate R? Because you'll only know the rewards of the states you have been in. Okay? You only know the rewards of the states you have been in. So you get an approximation T, approximation of R, and then from this you compute an approximation of V using dynamic programming. And from V you compute pi approximation. Using what? Normally, greedy policy. That means if you act as if this is the real value of the states. And then, since you know the actions, you can see which action would get you the maximally expected backed up reward from any given state. And that will give you the policy that you're supposed to do.
Can't be there a way in which we can bypass this T and R thing and directly calculate the value function?
No, let's look at this first. Okay? So, you have V and you got to pi. This is fine. And you almost have basically active reinforcement learning now, because you're changing pi. So now you use this pi to simulate, get more experience. And then recompute T and R, recompute dP, you get new V, you get new pi, you're in action. This is active reinforcement learning. The only issue is greedy. Greedy is fine if you are using V star. If you have optimal value function, the greedy policy with respect to the optimal value function is also optimal policy. If you have approximate value function, in particular your value function may not even tell you the values for some of the states. They have just not been felt yet. So you have a partial or approximate value function. And the greedy with respect to approximate value function is not necessarily going to be the optimal thing. This gets us to the celebrated, when you do greedy, you are doing exploitation. You are exploiting the knowledge you have to the maximum. Which is fine if your knowledge is complete. If your knowledge is not complete, you should also once in a while improve, do things just to increase your knowledge, instead of just exploiting the knowledge you have. So for that, you need exploration. And the problem is, you can have problems where the initial policy is such that The initial policy will give you rise to another policy, which gives rise to another policy, which gives rise to another policy, all of which will basically keep you away from a whole bunch of states. You never see them if you only do greedy optimization with respect to those value functions. So you need to walk on the wild side once in a while. You need to explore. You need to essentially do actions that are not greedy with respect to the policy, greedy with respect to the value function. Do you see that? Okay? That's so basically this is exploration versus exploitation trade-off. If you basically, the reason there's a trade-off is if you keep doing, you can overdo the exploration part. You can say, I mean, I'm not done yet, I need more knowledge. And so I will essentially do mostly random actions from any state. Okay? Or you can overdo the exploitation part. I'm done already. I'm, elementary school, I already graduated from the elementary school, so it's time to make some real money. Okay? And that's, basically going all the way to exploitation, ignoring the exploration. There are states of the world which involve you having like a PhD diploma that may be good. And you haven't even actually explored them. Okay? So that's what this one is basically showing, that if you actually happen to start with this policy, it turns out that since, remember, these are all these actions where if you do this, you will go with some probability here, some probability here, some probability here. So you'll never get into this. And similarly, this guy will never get into this. So these two states can have platinum, or gold, or diamonds, or ice cream, whichever you like. And you won't know. You're thinking you're doing active policy improvement, but you'll never even actually reach these states, and so you'll never be able to figure out their values, so you'll never be able to get optimal policy. You cannot be guaranteed to have optimal policy. You see what I'm saying? Okay? So that's a great problem with active reinforcement learning. You need to throw in a component of exploration on top of the exploitation. And exploitation is this whole thing. Convert experience to transition, transition to V to V, pi. Greedy pi. Okay? Now the question is, are you going to just keep using the greedy pi right away, or you are allowing to do some random things every once in a while? Exploration means basically doing random things once in a while. Okay? Now, when you are, and then so basically it turns out that the way you can be sure that reinforcement learning would reach optimal policy even in ergodic worlds. If it's non-ergodic, nobody guarantees anything. Even in ergodic worlds, the only way reinforcement learning will eventually find optimal policy would be if in fact you reach all the states that are reachable. If you visit all the states that are reachable. And in particular, you visit each state infinitely often so that you can really get a feel for the transition function. Because it may be that there are some very unlikely outcomes for some actions. And in the first 15 times of doing it, you don't see that happening. And so it's a bad action as far as you're concerned. But there's a small probability that in fact the good things will happen. And so you need essentially more, you need to be able to, so the only time you can actually guarantee the convergence is systems must explore in the, is that they need to be able to, explore every state infinitely often, visit every state infinitely often. That's what is required. And so in fact, but at the same time, as your knowledge increases, you should start exploiting it. If you do completely random things, then you are basically using all your knowledge. So for example, presumably, for students who are in PhD and are still expecting their parents to pay for their tuition, are not exploiting any knowledge they got to some extent. Right? Because after all, you at least know to do a few things, for example, as part-time jobs and so on. And so maybe you would do that while doing this exploration. That's basically the quote-unquote part-time PhD students might be doing that. Or at least you get some other university-paid job which does partial exploitation of your background. The knowledge that you got in undergrad is being used to get some money on the side while you are exploring more states. Okay, and you just basically, the only thing is that you need to become greedy to exploit your knowledge as you have more and more experience. Okay, and so it's like greedy in the limit of infinite exploration is the word that we use, glee, which is, all reinforcement learners should become greedy only after exploring a large amount of time. Okay, so to do that, we need some kind of policies, and we'll come back to the next class, but basically here are two simple ideas. One is essentially follow the current greedy policy with 1 minus epsilon probability, and do a random action, not decided by, basically, if you're in state S, okay, and the current greedy policy says do A, you do that with 1 minus epsilon probability. With epsilon probability, you do any of the actions that can be done. Those of you who remember GSAT in the satisfiability, conflicts, CSV things, you know that, for example, that sort of a thing was used there to avoid